So this is another natural response of an RL circuit. So we've got a 6.4 amp independent current source. We've got a switch that opens at t equals 0, and the switch is set up such that it'll be on one side or the other, but when it's traveling from one side to the other, there's no air gap, because for some kinds of current sources, if the circuit is opened and there's no place for the current to go, it'll keep trying to push the current through air, basically, which has a high resistance, and it'll arc. So this type of circuit, prevents that, because while it's switching, initially it'll be down here and connected to this side, but while it's switching for a brief moment, it'll be connected to both parts of the circuit, which is tolerable, but that only happens for, a brief moment while it's switching. So for the most part, it's connected to one side or the other, but the overlap on this little part here prevents the current source from being connected to nothing, which can cause arcing. So just a little kind of a detail thing. So there's a 10 ohm resistor here with V0 across it. There's a 6 ohm. Okay, then here's our inductor. It's a 0.32 Henry. And there's a 4 ohm resistor. So we want to find V sub 0 as a function of time. So the voltage across this 10 ohm resistor as a function of time for t greater than 0. So we want to find the percent of the inductor energy that's sent to this percent of inductor energy sent to the 4 ohm resistor. So the first thing we want to do is find the initial current in the inductor. So basically we need to draw the circuit at t much less than 0. So it looks like at steady state, way before 0, we can simplify this switch and just draw it over here like this. But I'm going to line up the components. You can tell what goes where. But the 10 ohm there, and the V0 is across that dude, and then there's our. So at t much less than 0, this inductor starts behaving like a wire again. So it's still there, but it's because the current is constant. And that's what happens with inductors. The current will just become constant over a long period of time with a steady state current source. So the voltage will be 0 because the current is constant and voltage is I prime. So this behaves like a short, like a wire. All the current's going through it, and it has 0 voltage across it, just like a wire. So the resistor over here for t less than 0, it's behaves as if it isn't there. It's shorted out of the circuit. So let's call this I. And although we strictly don't need it, it's nice. Well, yeah, we will need it. I sub 0, we'll put it on this branch. So these polarities, or these current directions, make sense right now because the current's going up, and it's going to come over here, and it's going to split across this resistor and split across this resistor and come on back down through the inductor that's behaving like a wire now. So, you're going to have some current coming down and some current coming that way. So these arrow directions make sense. We can find I, let's call this I at 0 because it's before 0 and up to 0. And we'll call this I at 0 as well. So let's use this notation here. The initial current through the inductor is often used. We often have this symbol, but that's basically just our little I at 0. And we can use current division here. I'm doing current division. This is current division. We're taking this 6 amps and splitting it across this guy and this guy. So it's going to be, I want the current opposite this 10 ohm thing. So this is the current division equation, right? The 6 ohm branch, the 10 ohm branch, and I want the current in the 6 ohm branch. So I put the 10 on the top, and the 6.4 is what's getting split. So this is 4 amps. So this is a number we're going to need. Now this is I at 0. This is the current through the inductor at 0. We need to know, or it's nice to know, the current through the through this 10 ohm resistor at 0. We're going to use Ohm's law to get this V sub 0, basically. So that's why we need this. So I sub 0 at 0, you can use current division again. This is just the 6 is going to go on the top. So this is going to be 2.4 amps. Okay. Now the next thing we need is we need the equivalent R seen by inductor for t greater than 0. So we're going to throw the switch. Oh, I have the arrow direction wrong. Shoot. So initially the switch is up and energizing this inductor. Current's coming around and going that way. And then at T0 we throw the switch down, which disconnects this 6.4 amp source. And it just takes it completely out of the circuit because they'll be two independent circuits only sharing this one node. So there's no return path for this guy. The 6.4 amp just drops out, and the circuit for t greater than 0 looks like this. V0 is still there, and this is the polarity that we previously assigned. Then the 6 amp is here. The inductor sort of comes back because now he's no longer constant. It's going to be an exponential decay function, and it's going to be driving its initial current out through these other guys. So this 4 ohm guy comes back. Okay, so this initial I through this inductor will, after the switch is thrown, the circuit looks like this. The I is going to be coming down this way, and it's going to be going up this way and this way. This I current's going to split at this node at the bottom here. Some's going to go that way and some's going to go that way. But right now we're asking, we need to find this R thing so we can get tau, the time constant tau. So what we need is the equivalent resistor. So this is a 10 ohm. So the resistance seen by the inductor is the 6, the 10, which are in series across these nodes A, B. And then 4 is across nodes A, B. So 6 plus 10, that 16 is in parallel with 4. So R equivalent, you could call it, is going to be 6 plus 10 quantity in parallel with 4, right? Because these 6 and 10 are in series and the 4 is in parallel. So this is 3.2 amps. So what we're saying is this inductor right here sees, it's going to behave as if it's connected to a 3.2 ohm. This is the 0.32 Henry. It's going to behave as if it's connected to a single 3.2 ohm resistor. So tau is L by R equivalent. That's going to be 0.32 Henries over 3.2 ohms, going to be 0.1 seconds. This is tau, which isn't an answer that they're asking for, but we're going to need it. So now we can find I of t. So yeah, just follow through here. So we're gonna find I of t, the current through the inductor. We have the initial current and we have the time constant and we have this formula I sub 0 e to the minus t by tau. So we can do an expression for I of t through the inductor. This initially has 4 amps through it, and then it's e to the minus t by 0.1 or 4 e to the minus 10t. This is amps. This is the current through the inductor as a function of time. So now here's a neat trick. We know this I through the inductor as a function of time, and we know that it's split. That is, there's voltage division going on, or this I of t is being split halfway that way and halfway that way. So we can find expressions for I of 0 as a function of time by using, we can use current division. So current division, we can use current division with functions of time, which is a new thing we haven't done yet. So I sub 0 of t is going to be, okay, you got to put a negative in here because I sub 0 is going down. That's how we chose it here. And here it was actually going down. It would have a positive value going down. But here, this I from the inductor is going to split left and right and then go up here. So we need a negative to account for that. So it's, this is I of t is getting current divided. Some goes through the 4 ohm branch, some goes through the 10 plus 6 ohm branch, and we want how much is going through the 10 plus 6 ohm branch, 10 plus 6 branch. So we put the 4 on top, so this is going to be, it's going to be 4 e to the minus 10t, which is I of t, times 4 over 20. Oh, I forgot the negative sign. Negative. So this is negative 0.8 e to the minus 10t amps. So we have I0 of t here, and we have I of t here. We can graph those. So we could graph those, but you know what? What we're trying to find is V0 of t, and we're almost there. So just by Ohm's law, you know, V equals I R. So V0 of t is going to be I0 of t times R, or which is R is 10. So it's going to be minus 0.8 e to the minus 10t times 10. It's going to be minus 8 e to the minus 10t. Units are volts. So we have I of t, I0 of t, and V0 of t. Let's graph them. So V0, I0, the current and voltage on the 10 ohm, And then we've got I, the current through the inductor as a function of time. So the current through the inductor is 4 e to the minus 10t. So it starts out at 4, and because it's an inductor, it's not going to have a step change. So it's going to look like that. So the current before 0 is 4, which is what we solved up here. And then the current after 0 is 4 e to the minus 10t. It goes down like that. Okay, the I0 of t is minus 0.8. So it's minus 0.8 amps, and then it decays to 0. That's what this function here is saying. But the current before the switch is closed is 2.4 amps, so it has a jump, which is fine. It's just a current. I sub 0 is the current through the resistor, which can jump. That's no problem. It's the current through the inductor that can't step change like that. So this is cool. The current through the resistor here switches directions when the switch is thrown. That's fine. Okay, V0 of t is minus 8, and then decaying down to 0. That's this equation here. And then so the voltage before the switch is thrown, it wasn't, we weren't asked for that, but we can figure it out. Just for fun, the voltage V sub 0 at t, at t less than 0, that's going to be, well, we know that it's got 2.4 amps in it. Steady state. This thing has 2.4 amps going down from plus to minus here. So it's, by Ohm's law, it's going to be V sub 0 is going to, at 0 minus, which is another way of saying t less than 0, is just going to be 10 ohms times the 2.4 amps. It's going to be 24 volts. So this thing has 24 volts with this plus to minus polarity. And then, current's going down. And then the switch is thrown, and the current starts coming from the inductor in the opposite direction. So the voltage polarity, goes to -8 in reference to this plus minus. And yeah, that's what's happening there. So that's this is the answer right here, what they were asking for, V0 of t. All right, then the next thing they want is the percent of the energy sent to the 4 ohm inductor. Okay, here we're going to do this the hard way, just to look at some concepts. So this is okay, there's a lot of fun stuff going on here. So look, we want to find the percent of the inductor energy sent to the 4 ohm resistor. So we're going to need to find the initial energy, and then energy at, so they want to know the percent of the energy sent to the 4 ohm inductor. So we're going to find the total energy that was charged up into this inductor, right? And then they threw the switch, and some of the current went this way and some went that way. So some of the energy is dissipated in here, and some of the energy is dissipated in here. So there's about a bunch of different ways that this could be solved, but what we're going to need the energy in here, the total energy in here, because they're asking how much of that total energy went to the 4 ohm inductor, right? They're asking what percent of the inductor energy was sent to the 4 ohm inductor. So we're going to need the total energy. So the W in the inductor at 0 is just going to be 1/2 Li at 0 squared. So it's going to be 1/2. This is a 0.32 Henry inductor, and it had 4 amps initially in it, right? We figured that out here. That was the initial, at steady state, this thing ended up with 4 amps in it. So this is 2.56 joules. That's the initial energy in the in the inductor. Okay, now here's where it gets fun. We solved for V sub 0 using Ohm's law because we solved for I sub 0 and then we got V sub 0. We could do that here. We could solve for the voltage across the 4 ohm because we want to know the power sent to the 4 ohm. We could solve for the voltage across the 4 ohm as a function of time. We could do that just by using current division like we did here and find the current division on this side and then use Ohm's law here. We could do that and that would work, but another way to do it is to note that power is V squared over R. Power in a resistor is given by V squared over R. So this could be a function of time. So power as a function of time is given by voltage as a function of time squared over R for a resistor. So if we had this voltage as a function of time, we could use this. Now, like I say, we could have done that. We could have found voltage as a function of time the same way we found it over here. But just to have more fun, we're going to find it in a different way. But I guess I'm skipping something. So if we had power as a function of time, if we had power in the 4 ohm as a function of time, given by power in the 4 ohm as a function of time squared over R, just what I wrote over here, just a little bit nicer, then the energy in the 4 ohm, the total energy would be integrating this power, integrate P of t from 0 to infinity. We would get there's going to be some curve, right? And we want the area under the curve. So if we had the power in the resistor as a function of time, we could integrate it into the curve and get the energy as a function of the total energy, regardless of time, just the total energy, and then compare that to the energy that was in the inductor. So here's so basically we need V in the 4 ohm as a function of time. Then we're going to plug it into this formula here and get power in the form as a function of time. Then we're going to integrate from 0 to infinity and get the total energy sent to the 4 ohm and then compare that with the W. That's what we're doing. So we need V, the 4 ohm, a function of time, and we're going to do this the hard way, not by current division and Ohm's law, but we're going to do it by note that the voltage across the 4 ohm resistor is the voltage across the inductor, because these are in parallel. This 4 ohm resistor is in parallel with the inductor here. So they have the same voltage across them. And we have a formula for we have this. The voltage across an inductor is Li prime. So, and Li is I. The voltage across an inductor is L times the current through the inductor. I'm just going to have this polarity, by the way. So yeah, so this is just going to be this is just going to be 032. That's L, and then I prime is going to be minus 40 to the minus 10t. That's it's this guy. The derivative of this guy is this guy. So you're gonna get minus 12.8 e to the minus 10t volts. This is the voltage across the 4 ohm as a function of time. So now we can get power across the 4 ohm resistor as a function of time just using this V squared over R. So it's going to be minus 12.8 e to the minus 10t squared over 4, V squared over R. So it's going to be 40.96 e to the minus 20t. So we can graph that just to not get too crazy. So this thing starts out at 40.96. This is the power in the 4 ohm as a function of time, and it goes on down like that. And we want the energy to the 4 ohm. The total energy sent to the 4 ohm is the area under the curve. So the energy in the 4 ohm is the integral from 0 to infinity of P of t. It's 40.96 e to the minus 20t dt. If you work that all out and plug in and plug in, you're going to get 2.048 joules. There it is. So the percent to the 4 ohm is going to be 2.048 over the total that was in the inductor, right? This is the amount that went to the resistor. This is the total amount that we solved up in here that was available in the inductor. So this is like 80%. So that should sort of make sense that it's 80%, because if you compare the resistor ratios, like this I, which sort of represents the energy in the inductor, some goes that way and some goes that way, and most of it goes this way. 80% of it goes this way. And if you look, this is 16 ohms on this side and 4 ohms on this side. So this is like a 4 to 1 ratio, which you know, sort of makes sense that it would be most of the energy going in here, because most of the current would go through this lower resistance branch. Okay.